So element C, right, is exactly at the, if you look at element C, is exactly at the centroid. Am I right? Element C is exactly, yeah, element C is at the exactly at the centroid. So we know the formula is equal to what? Vz over Iz. So we have to calculate Qz. Right? We have to calculate Qz. So Qz, so when that's the case, this will be our width, right? This will be our depth. Okay. So again, specifying which is your width and depth can really help. And I might need the geometry, which will help me a lot. Okay, so I need this geometry. Okay, so the axis of interest, because it's IZZ, so this will be our width, and this distance will be our depth. Okay, so let me see. This is our Vx, right? So it's ZZ. Okay. Why I say that's our width? Because now if you look at Vx, the axis of interest is what now is our what? ZZ. Okay. Right. So now I'm going to break this up. So this is where you have to be very careful. Okay. I'm going to break this up here and here. Right. So the width is equal to 2.5 and the depth is 0.25. Let me check again. The width, yep, the depth 0.25. The y bar is 3 minus by 0.25 divided by 2. Okay. And then plus twice left and right. The width now is 2.5 0.25. The depth now is 3. The y bar now is 3 divided by 2. Okay. So y2, because there's a left and there is a what? A right. Okay. So this is equal to 3 minus 0.25 divided by 2 times by 0.25 times by 2.5 plus by 2 times by 0.25 times 3 times by 3 over 2 is equal to 4.047 inches cube. I'll do it again. 3 minus 0.25 divided by 2 equal times by 0.25 times by 2.5 plus by 2 times by 0.25 times 3 times by 3 over 2 is equal to 4.047. Okay. So that is our QZ at point C, where point C is here. Okay. So from here, I can find QZ. So the next one, I'm going to look for our QX. Right. So we know at QX, right, seeing how so point C is here. This is the terminal. So QX is equal to 0 for element C. Okay, I do apologize. I need to find that this is element C. Okay. So when this is the case, we can find our shear already. Okay, so our shear is equal. So we know that this term is equal to 0 because QX equal to 0. So Vx is equal to 3000 multiplied by 4.047 divided by IZZ. Not a clue what is our IZZ. Our IZZ is 19.399 or 19.339, sorry. Divide by the thickness of 0.25 and its box beam, that's why we include the 2. Okay. So 3000 multiplied by 4.047 divided by 19.339 divided by 2 is equal to 1.255 or 1.256. 1.256 times 10 to the power 3 psi. And because of the direction, right, you can see the direction over there, we have to specify the direction is going towards the right. Okay, so 1.256 going towards the left, dependent on the shear flow. Okay, now this is where you have to be really careful and also remember the concept of thin-wall analysis. Okay, now let's do the next one. Okay, point B. Point A is easy. Point A is equal to 0 because it's at the corner. There's no area at a corner, so that's the easy part. Okay, now let's look at point B now. Okay, are we okay down here? Any question to ask about this?
Can you explain why you use 2Q?
Because it's box beam analysis. One Q go one side, the other Q go the other side.
Oh, okay, yeah.
Okay, it's just a
How
box
do we
beam.
know to treat it as thin wall analysis, though?
Hmm?
Like, how do we know to treat it as thin wall analysis?
I will tell you in your exam.
Okay.
Okay, I will not make you guess, especially in the exam. I will tell you like your term test, right? Apply thin wall analysis, apply non-thin wall analysis. Okay. Right. Now, in fact, you know, Felicity, you asked a very good question. But believe it or not, if it's non-thin wall analysis, the answer will be the same. Okay, I will tell you that, Felicity. If it's non-thin wall analysis, you take this, you take the same area over here, right? For non-thin wall, you take the same area and you still divide by the same thickness, 0.25 divided by 2. Your answer will still be the same. Okay. The only thing that is different if it's non-thin wall, this will not be 0 if it's non-thin wall. Wait, let me see. No, you'll still be 0. If it's non-thin wall, it will still be 0. It will flow. No. Yeah, you'll still be equal to 0 because it's at the surface. Okay. Okay. So if you revise your thin wall and non-thin wall, your QZ still be the same. Your QX also be the same. Either you use thin wall or non-thin wall analysis. Okay. Right. Now I got you guys worried. Like, oh no, thin wall and non-thin wall are involved again. That is why you asked me to do this example. I think. Right. So I'm going to copy this. Okay. So next you want to look at point B now, element B. Okay. So we know that the formula. Okay, I'll copy the formula across. Or I can just write down. So the shear is equal to Vx over Izz Qz divided by T plus by Vz over Ixx Qx divided by T. Okay. So we look at element B now. Okay, so if it would really help if I have this figure. Right. So we know that element B is a certain distance away, right? It is like 0.25 from the edge. So if I were to draw the cross section, we know this is our exact location for element B, because this distance to this distance is equal to 0.25. Okay. So now we want to find our Vx, and I want you to look at the direction of the shear flow. Okay. Right. So this is our ZZ, and this is our terminal. Right. So this will be our width, and this will be our depth. Okay. So we know that QZ is equal, so we have to consider this entire area now. Okay. So the width is 3. The depth is 0.25. The y bar is 3 minus by 0.25 divided by 2. Okay. So 3 minus 0.25 divided by 2 times by 0.25 times 3 is equal to 212.156 inches cubed. Okay, so let me do it again. Times by 0.25 times by 3, 2.156 inches squared. Okay, so that is our QZ. So next we want to find our QX. Right, so I'll draw this figure again. So this is because of VZ, right? Terminal here, the shear flow move this way. So over here, this is where we have our element B, right? And then this is relative to the x-axis. Why x-axis? Because if you look at the formula, VZ over what? IZZ, right? So this is the area that we have to consider. Again, is box beam. Okay, so this is our width, and this is our depth. Okay, so the width is equal to 5.5. The depth is 0.25. The y bar is 3 divided by 2 minus by 0.25 divided by 2. Okay, so the width, I got it right. The depth, I got it right. The y bar is 3 divided by 2, 0.25 divided by 2. Okay. So this will be equal to 3 divided by 2 minus 0.25 divided by 2 times by 0.25 times 5.5 is equal to 1.891. I'll do it again. So 3 divided by 2 minus 0.25 divided by 2 times by 0.25 times by 5.5. 1.891. Okay. Now, the careful thing is this. If we look at, I'm going to draw the shear flow, right? Or I've already done the shear flow, right? You can see two different directions at element B. So this is element B. Over here, this is element B, right? This one is going towards the left. This one is going towards the right. So it's up to you to decide what is plus or what is minus. But they both cannot be plus. One has to be plus, one has to be minus. Because one arrow is going towards the left, the other arrow is going towards the right. Okay, so all you need to do now is you do Vx. Okay, so the shear is equal to Vx is equal to